Okay. Note, in order, if we wanted to allow the odds ratio for males versus females to depend on ECG status, what would we have to do? What did we learn in multiple linear regression that we'd have to add to our model to allow for that? We can get more complicated here. I'm not going to take it this far in this class because we're getting fairly complicated already. But if we wanted to allow the odds ratio for males versus females to depend on ECG status, which it might, we could add an interaction term to our model. And I'm not going to have you do that for this class. And as you can see, it blows up our little model. It doesn't quite work. Some of you might want to try doing that for your projects. So I'm going to leave it at that. And instead, what I'm going to do is we can also get predicted probabilities directly from our model statement or from our proc logistics statement. And so what I'm going to do is add some code here. Output out equals predict. This is my dataset name. Okay. Pred equals prob. So I'll explain this more in the notes. But I'm asking for the predicted probabilities to come out of this data set. And then I can say proc print data equals predict. This will create a new data set called predict that holds my predicted probabilities, and run. Let's just see what I get from that. And so now I get this table of predicted probabilities, which is clearly not correct. Oh, because I was wondering why that was so weird. I never said freak count in my proc logistic. I have to tell proc logistic that I'm using summary statistics. So you see, even I make that mistake. So you have to be careful that you don't leave out the freak count. So now let's go back to the notes and let me tell you what this all does. So this is basically what I've already said. And the code I added to my previous proc logistic run is simply this output. And this is going to create a new data set creates a new data set that I'm calling, this is my name, I'm naming predict. You can call that whatever you want, but I'm naming it predict. Okay? And my predicted probabilities, which are in the SAS name pred, I'm calling my variable name is prob. But again, this is my variable name. I can call that whatever I want. Okay? And when I print this, this is what I get. So I get my, you can see I get my, a breakdown by my explanatory variables, sex and ECG, and I have cells for each combination of explanatory variable plus each combination of coronary artery disease. And the thing that's a little strange about this, and you see I also get the counts that are in each of these cells. So we had 4 females with low coronary artery disease, with low ECG and coronary artery disease. We had 11 in those categories with no coronary artery disease, and so forth. So these are just the same data that we saw before. It's telling me that I'm modeling the yeses for CAD. And then the predicted probabilities, note that it replicates the predicted probabilities because, again, I'm modeling the probability of a yes. So even for the no cells, I'm still modeling the probability of a yes. So that's why my predicted probabilities are the same for each of these. And you'll see that that gets replicated. Can you verify the predicted probability of CA disease for female patients with low ECG scores? So remember that the p hat, the predicted probability, is my odds at x over 1 plus the odds at x. And if you recall, the odds for females with low ECG, from back here, the odds for females with low ECG was 0.3089. So this would be 0.3089 divided by 1 plus 0.3089. So odds over 1 plus the odds. And if you do that calculation, you'll get 0.2358, which, subject to rounding, but it basically is the same as that. What about for male patients with a high ECG? Well, for male patients with a high ECG, the odds were 3.1797. So for this subpopulation, male patients with a high ECG, we can put in 3.1797 divided by 1 plus 3.1797. So you can see that's about 3 over 4, so we know it's going to be about 0.75. It turns out 0.7613, which again corresponds pretty close to what we have here, just subject to rounding. So that's where these predicted probabilities are coming from. So we can get SAS to output those predicted probabilities. So I want to finish up this set of notes by talking about model assumptions, evaluating logistic regression assumptions. And remember that for linear models, we had the line assumptions. We don't quite have the same assumptions for logistic regression. Some of the assumptions are similar. You can see I started spelling out line again, but the L in this case actually stands for large sample size. That's sort of the most important assumption for logistic regression. And why do we need a large sample size? The reliability of these test statistics that we're using and the confidence intervals all rely on being able to use z-scores. And the reliability of those z-scores means having sufficiently large sample sizes. As I mentioned here, for small sample sizes, the z-tests tend to result in type 1 error rates that are too big, basically. So the typical rule of thumb that we want is we want at least 10 observations for the rarer outcome, whether that's zeros or ones, per parameter in the model. So if we look back at our CAD data, we want at least 10 observations for the rarer outcome. So we have more than 10 observations in each of these. But we want at least 10 observations for each parameter that we're going to put in the model, other than beta 0. So here we're going to put 2 parameters in the model, so we would want at least 20 observations for each the diseased and the no disease category. So we're fine there. So as our example, with 2 slope parameters, we want at least 20 observations for both y equals 0 and y equals 1, so we're fine there. We also want independence of responses, just like we did in linear regression. And as we saw there, this assumption is actually still best evaluated by considering the study design and trying to identify possible sources of non-independence. So similar to what we saw in the Chapter 3D notes. Multicollinearity is still a concern if we're using multiple logistic regression. And there's no simple way to assess that in logistic regression. The best thing to do, I think, is just to look at a correlation plot of the explanatory variables to see if we have any extreme correlations. We could also fit a linear model with our 0, 1 variable as the response to see if we get any high VIFs, but I won't go into that here. Linearity is also a concern, but now it's linearity with respect to between the logits and the explanatory variables. And there are ways to check that, but that's beyond the scope of this class. We're just doing an introduction to the logistic regression here, so I won't get into that. But the last assumption I do want to talk about a little bit. Excuse me. The last assumption is that the model provides reasonable fit to the data. And that we're going to assess through a goodness of fit test. And the goodness of fit test, there are different goodness of fit tests that we can possibly use. I'm just going to talk about one in this class. So these are tests that we can use to assess a model's goodness of fit. And I'm just going to talk about one named by these two statisticians, Hosmer and Lemschel. And I just want to pause this. So Hosmer and Lemschel are two statisticians, and they came up with this test, so they get to be named for it. And we can do this in SAS by using lack fit option on the proclogistic model statement. Okay, I'll show you that in SAS. So we can do that in SAS actually with our same data set here. If we just say lack fit on the model statement, that will provide us with this extra Hosmer and Lemschel goodness of fit test, which I'll talk about here in the notes. And it's similar in a way to the nested F test, because the hypotheses are that the current model fits well versus the alternative that the current model does not fit well. Okay. Clearly, we want the null hypothesis to be true, right? That's what we want. So we desire to not reject the null hypothesis, which is typically what we want for all goodness of fit tests. But as usual, something to keep in mind, not rejecting the null hypothesis does not mean that the null hypothesis is true. It just means that we don't see any serious, egregious departures from the null hypothesis, so we feel comfortable proceeding as if the null hypothesis is true. Okay. So what the Hosmer and Lemschel test does is it partitions our data into subgroups with similar model predicted probabilities. And the test then compares the number of observations for each value of the response variable in each subgroup with the expected number of events based on those probabilities estimated by the model. So, just to remind you, our model predicted probabilities, for our data set, we only have 4 different model predicted probabilities, because we only have 4 different combinations of the explanatory variables. Females in low ECG, females in high ECG, and so on. And so what the Hosmer and Lemschel test is going to do in our case, it splits the data into subgroups with similar model predicted probabilities. Well, we only have 4 of them in our case, so that's why we're going with 4 groups here. And just to remind you, so Hosmer and Lemschel test does this automatically in SAS. Group 1 has 15 observations. Well, group 1, 15 observations are just going to be the females with low ECGs. So this is females with low ECG. Okay. And then 18, that's going to be our females with high ECG. And we also have 18 males with low ECG. And so that's where these numbers are coming from. So this is females with high ECG, females or males with low ECG, and males with high ECG. And you can verify that by the breakdown of the CAD equals yes and CAD equals no's, the observed counts. So what the Hosmer and Lemonisheau test does is it compares the observed counts in each cell to the expected counts. And the expected counts can be, so the expected CAD equals yes. We have 15 observations here, 15 times whatever our p hat of x was there. And if you look back at the previous page, the p hat from our model is 0.23601. So that'd be 15 times 0.23601. And if you do that calculation, you'll get 3.54. So that's where that expected value is coming from. And similarly, we can do the expected with the nose from that cell. Expected CAD equals no. Again, there were 15 total observations of females with low ECG. The probability, the estimated probability of having no ECG in that cell is just 1 minus p hat of x. So this would be 15 times 1 minus 0.23601, which again, if you do that calculation, you'll get 11.46, which is where that value is coming from in the table. So this is what SAS is doing to calculate the Hosmer and Lemonisheau test. And that's where all these expected values are coming from. And then the test just compares the observed counts in each cell to the expected counts in each cell. So we observed 4. According to our model, we expected 3.54. We observed 8 here. We expected 8.46 according to our model, and so forth. And there are 8 different cells here. So what the chi-squared test does is it sums over all 8 of our cells, and it takes the observed cell count, the OI, which here is 4, minus the expected cell count, squares that difference, and divides by the expected cell count. And you can do that for yourself. Take 4 minus 3.54, square that, divided by 3.54, and do that for all 8 of these cells. And when you add that up, you'll get 0.2155. The degrees of freedom is going to be the number of groups, which in this case is 4, minus the number of model parameters, the non-intercept model parameters, which in this case is 4 minus 2, or 2. That's where this is coming from. And then our p-value. So I don't care so much whether you know how to get this test statistic, but I thought it would be interesting for some of you to see how this is done. It's not magic, it's all just math, right? But once you get your test statistic and once you get your p-value, we're in p-value world here, so even if you didn't follow along with how I calculated that test statistic, you know what this p-value means. This means do not reject. And since our do not reject the null hypothesis, and since our null hypothesis here is that the current model fits well, that's what we want to see. So that's a good thing. That's what we want. That doesn't mean the model is perfect, doesn't mean the model is even close to right, but it means that with respect to our data, we don't see any evidence that the model isn't okay. And so I'm going to have you conduct this test. I probably won't have you actually write out the test statistic, but I thought it might be interesting. So that's the end of these notes. And we will continue on.